Okay, thank you all for your attendance. My name is Peter. I'm part of the research and development team at Oz Diagnostics, and we're an Australian-based developer and manufacturer of IVD diagnostic devices. And today I want to present an overview of one of our key technologies, the Oz Diagnostics Multiplex Tandem PCR method, and also highlight a few real-world applications of Multiplex Tandem PCR, or MT PCR as we like to call it, as a molecular diagnostic method. So in this presentation, I would like to cover the basic principle of the MT PCR method. I'll provide a few practical examples of its application, specifically looking at its application as a syndromic testing method. Then we'll also look at a few other real-world applications of MT PCR, including SNP typing to infer the presence of a SARS-CoV-2 variant of concern. And then we'll have a look at MT PCR for the identification of common STIs, including resistance markers for ceftriaxone, fluoroquinolone, and macrolide-based antibiotics. Then I'd also like to share one final example of MT PCR applied in diagnostic mycology, more as a time saver than anything else. So just starting with the whole concept of syndromic testing, the main idea of syndromic testing is really just to remove some of the uncertainty that might be present within a clinical diagnosis. So, for example, if a patient presents to a clinician with a set of fairly non-specific symptoms, say something like a headache, cough, or a fever, or something along those lines, a clinician could probably make a presumptive diagnosis that their patient probably has a respiratory virus of some sort. But the question, of course, is which respiratory virus? You know, it could be something that's usually mild, like rhinovirus, something a little bit more serious, like influenza, or it could be something that's currently a public health risk, like SARS-CoV-2, or something else entirely. We really don't know until we test for it. Now, in the current pandemic environment we find ourselves in, distinguishing the actual causative agent in such cases is really now more critical than ever. Not just for the patient and for patient management, but for the safety of the community as a whole. And this is where syndromic testing really makes sense. The advantage, of course, for the clinician is that they don't actually need to specify every pathogen that they suspect on their pathology request form, and potentially risk missing the causative agent. They could simply order something like a respiratory PCR or a respiratory screen and know that they're covered for the majority of cases out there. So once the results come back and the causative agent has been identified, hopefully this can provide the basis for a more precise diagnosis, which hopefully should lead to better clinical management and better clinical outcomes. Well, the ability to test a patient for a broad collection of pathogens, is a great tool for the clinician. It can really pose some logistical challenges for those of us in the lab actually performing the tests. For this kind of thing to be practical and cost effective, such testing really needs to be applied in a large kind of multiplex format, preferably one large multiplex with as little hands-on time as possible. And this is where MT PCR really fits in and where MT PCR really stands out. So for those that aren't familiar with the technique, MT PCR is a highly multiplexed diagnostic method developed by Oz Diagnostics, which allows labs to simultaneously test for multiple pathogens from a single starting sample. So this slide gives a basic overview of the MT PCR process. So as you can see, it's a two-step process with two separate amplification reactions. Now, step one is where reverse transcription occurs and what we call sample enrichment. Step two is then another amplification step followed by detection. So let's have a look at each one of these steps in a little bit more detail. So starting with step one, in step one, the first thing that happens is that the sample is added to the reaction tube along with the master mix. The first step that would occur is a reverse transcription is performed. The sample is then enriched in a highly multiplexed limited cycle reaction containing a collection of primers for all the pathogens of interest. Now, depending on the application, this can be anywhere from 8 to over 30 assays in a single reaction. Now, the low number of cycles used in a step one reaction, this is normally around 15, really does minimize the formation of any non-specific product, as off-target reactions don't really have enough cycles or time to become established. Now, the main benefit of doing it this way is that only a single 10 microliter sample is actually needed, even when assaying over 30 targets. So upon completion of step one, if any of the pathogens were present that we're assaying for, the amount of those pathogens now present in that sample is greatly enriched. Of course, the majority of this process is actually quite automated, with the user just needing to place their plate or tubes of extracts along with the consumables on the processor and hit the start button. So currently we have 2 robotic platforms for this. The top image there is our high-plex instrument, which can perform up to 24 MT PCR reactions at a time. And the lower image is our ultraplex instrument, which can process up to 96 MT PCR reactions at a time. So that's step one in a nutshell. Let's move on to step two. Okay. So in the step two reaction, the product of the step one reaction actually becomes the sample. So the first thing that happens is the step one product is diluted. This provides us a clean basis or a clean sample that's made up predominantly of targets that were identified in the step one reaction. This is then split into multiple singleplex or duplex reactions across a 3 to 4 well plate. As the primers used in step two are actually positioned within the product of the step one reaction, this really gives MT PCR a greatly improved specificity, as effectively 2 separate PCR reactions are needed for successful detection. Okay. So step two then proceeds, as you'd expect, as a standard real-time reaction, with the analysis of each step two reaction performed through a combination of CQ and also Mel curve analysis, with integrated software providing a call for each step two reaction. So what is the benefit of this technique? MT PCR has a number of advantages when applied to in vitro diagnostics. Firstly, and probably most importantly, the capability to perform a very large multiplex reaction from a single sample really does lend the technique very well to comprehensive syndromic testing. MT PCR is also quite specific, as 2 separate assays are needed for successful detection. The technique is also very sensitive, only needing around 10 copies of reaction or less in most cases. And in practical use, MT PCR also needs minimal hands-on time, as setup is performed by an accompanying robotic platform that we showed earlier. And MT PCR is also quite flexible when it comes to throughput. We currently offer MT PCR that can range anywhere between 1 to 96 samples per run. And it's also capable of being applied to some more specialized PCR applications, such as the detection of SNPs or insertions or deletions. So now we've covered the basic principle, I want to share with you some real-world examples. So this first case is taken from our respiratory pathogens 24-well panel, which detects 28 different respiratory pathogens and also has 2 integrated internal controls. And this is what the output would typically look like. So just so this makes sense, this is looking at the results of a single sample within the run. The list on the left displays all the pathogens that were tested and if anything was detected. So from the top, we have influenza A and B, pneumocystis, 2 different assays for SARS-CoV-2, of course, chlamydophila psittaci, RSV, and so on as we continue down the list. The cycling curves and melt curves are displayed there on the right. The top graph being the cycling curve, which displays the fluorescence on the y-axis versus the cycle number on the x-axis, with the lower graph being the melt curve, which displays the change in fluorescence on the y-axis with respect to the temperature on the x. So looking at the results now, we have a positive here for parainfluenza 1 virus, which is the orange curve. We also have 2 positives that are internal controls. The black curve there is the inhibitor control. So as the name suggests, this informs the user if the reaction has proceeded normally or if it's been inhibited in some way. It does this by having a defined CQ range in which it should be positive. So if it falls outside this range, this is an indication of inhibition within the reaction. And obviously this is going to be flagged to the user and may also warrant a re-extraction or repeat of the testing. Now the purple curve there is our sample adequacy control. So this control looks for the presence of human DNA within the sample. And what this does is it informs the user really of the quality of the sample collection. So if we think about it, if there is no human DNA present within the sample, this indicates to the user that the sample collection, this is a swab we're normally talking about, was probably not performed correctly. So this might warrant a recollection request from the lab. In this particular case, though, it looks like the collector was exceedingly thorough. And yes, if you're wondering, all pathogens can be detected simultaneously from a single sample at the same time without any issues. Okay, so in addition to syndromic testing, the next application I'd like to present is MT PCR used for SNP discrimination. So this is a case taken from our SARS-CoV-2 typing panel. Now this panel identifies the presence of SARS-CoV-2 along with 6 point mutations and 1 deletion in the surface glycoprotein associated with SARS-CoV-2 variants of concern. Now specifically it's looking for the presence of N501Y, K417N and T, E484K and Q, and P681R mutations, along with the HV6970 deletion. Now, all of these are mutations that are associated with SARS-CoV-2 variants of concern. So in one aspect, the SNP pattern can be used to either alert to the presence of a variant of concern, but it could also be used to infer the variant present. So similar to the previous example, this panel also has 2 internal controls included. One is an inhibitor control, and another is a human RNA control, which plays a dual function. One aspect is a sample adequacy control, and as a second function as a reverse transcription control. So this is what an output would typically look like. Again, this is looking at the results from a single sample out of the run. Like the prior example, the list on the left displays the variables this panel is testing for, which in this particular panel can really be grouped into 3 separate sections. So we have a section for SARS-CoV-2 detection and confirmation, a section of assays for SNP typing, and then a section of assays for controls. So as in the prior example, the cycling curves and melt curves are displayed on the right. Unlike the prior example, however, there's a window in the bottom left that provides more direct interpretation of the results to the user. So if we have a look at that box now, that's the box in the bottom left of these results. It informs us that SARS-CoV-2 is present, confirmed by 3 separate assays, targeting ORF1, ORF6, and ORF8, so that's our SARS confirmation. We also have N501Y detected, and the HV6970 deletion is also present. All other positions here examined are reporting as wild type, except amino acid position 681, which here is reporting as other. So it's not the wild type, it's not P681R, which informs us it's another known mutation of this position, namely P681H is likely present. So in this case, we can then use the SNP pattern to infer the variant present. So as you probably guessed from the title of the slide, this SNP pattern is fairly indicative of the alpha variant. So we'll be able to infer with a good deal of confidence that the sample we have is an alpha variant. So how do we actually infer the variant present from the SNP pattern? The way we do it is we can actually apply the obtained pattern of mutations to a matrix of known SNPs in each variant to derive the variant present. So this table is a little bit busy, but I'll try to break it down for you. So each row here is a variant. The first 3 columns identify the variant lineage, the WHO's media-friendly label for that lineage, and also if this lineage is considered a variant of concern or a variant of interest, currently as specified by the WHO. The following 5 columns then display the known genotype of each variant at each amino acid position assessed. It's then really just a matter of matching the obtained SNP pattern to infer the variant detected. So just taking the example that we gave in the previous slide, so we had N501Y detected, we also had HV6970 deletion detected, and we've also inferred that P681H is also present. So if we have a look column by column, we can see N501Y is present in the alpha, beta, gamma, theta, and mu variants. If we then have a look at HV6970, this is present in the alpha variant, and it's also present in the eta variant. However, only the alpha variant has N501Y and HV6970 together. We can then keep looking through the SNP pattern and make sure the rest of what's being reported matches. So here we also have alpha, a wild type of position 417, a wild type of position 484, and P681 is reporting as P681H. So the SNP profile that we've generated matches the SNP profile that you'd expect to see in an alpha variant. So again, we can then infer with a good deal of confidence that the sample that we have is an alpha variant. So just one more example of this, just to kind of reinforce the point. In this sample, we've got SARS-CoV-2 again is present, again confirmed by 3 separate assays targeting ORF1, 6, and 8. So for this, I'm just looking in the little diagnostic box in the bottom left corner. Now, all positions examined in the sample are wild type, except amino acid position 681, which was reporting as P681R. And once again, as you've probably already derived from the title, this SNP pattern is fairly indicative of the Delta variant. But don't take my word for it, we should check against the matrix to be sure. So once again, we can have a look through, and the only variant that we have here that matches wild type at 501, 6970, 417, and 484, and also has a P681R mutation, is indeed the Delta variant. So once again, from the table, we can infer with a good deal of confidence that the sample we have is in fact a Delta variant. Now, of course, due to the rapidly evolving pandemic situation we find ourselves in, this panel and this matrix in particular is something that's going to be continuously updated as new variants emerge and new data becomes available. Okay, so let's shift to something a little bit different. This next case is taken from our urogenital and resistance panel. So this panel detects common STI pathogens such as chlamydia, gonorrhea, and mycoplasma. And it also informs of ceftriaxone resistance in Neisseria gonorrhea and fluoroquinolone and macrolide resistance in Mycoplasma genitalium. So once again, this is looking at the results from a single sample taken from the run. So similar to the previous examples, the lift on the left displays the variables the panel is testing, with the cycling curves and melt curves displayed on the right. Like the SARS typing example, there's also a window in the bottom left that provides an interpretation of the results for the user. So in this particular case, we have a positive for gonorrhea, which is the green curve. And if you're wondering why there are actually two green melt peaks, it's because gonorrhea is actually confirmed by two separate assays here, one targeting OPA-J and one targeting OPA-H, I believe, both of which are in the same well, so just for confirmation. So the blue curve here is for ceftriaxone resistance. And we also have two positives that are the internal controls. So once again, the black curve is the inhibitor control, with the purple curve being our sample adequacy control. Now, as I already mentioned, there's a window in the bottom left that provides an interpretation of the results. So in this case, it tells us that we have a patient that is positive for gonorrhea. And more importantly, it is also identified as ceftriaxone resistance. Now, this is all vital information that, when provided to a clinician, can really help guide an appropriate treatment for this particular patient. Now, there's just one final example I'd like to share with you. Now, this case is taken from our dermatophytes 12-well panel. Now, so for those that might not be familiar, dermatophytes cover a broad set of fungal species responsible for infections of the skin, hair, and nails mainly, more commonly referred to as tinea or sometimes ringworm. So you can have, tinea captis, which is the infection of the scalp, tinea corpus on the body, and so on and so forth. Now, while I'd expect the majority of clinicians out there to be able to diagnose such infections really without the need for pathology, a lot of the times samples are still going to be sent to the lab just for confirmation. Now, this is actually a requirement from the PBS if treatment with terbinafine is actually intended. So from a lab perspective, these are really not that difficult to process, but the one thing that can be is very, very time consuming. So a typical protocol would usually involve something like microscopy for initial verification, followed by culture to confirm the species present. So a turnaround time for this kind of result is not normally that rapid. The main reason is dermatophyte culture typically will take about 3 weeks to complete. Now, as you can imagine, 3-week culture time, you're going to need a lot of staff time to manage the cultures, as these obviously have to get checked on a regular basis for growth, and then proper typing performed once growth has been established. Now, this can be a bit of an issue, especially when dermatophyte confirmation requests can be quite a common task for the mycology lab. So, it's not unheard of for labs to have thousands of these requested a year or more in some cases, which they have to process. So this is where MT PCR can be applied really as a real time saver in this kind of situation. So something that once took 3 weeks to report can now be reported the same day. So having a look at an example run. So once again, this is the results looking from a single sample, looking at a single sample in the result, in the run file. Similar to the previous examples on the list on the left displays the variable the panel is testing for. So from the top, we have Trichophyton species, then the Trichophyton rubrum complex, the Metaprophytes complex, Microsporum species, and then Microsporum canis, and so on, as we go down the list. Once again, we've got the cycling curves and melt curves displayed on the right. So looking at the results, once again, the black curve is our inhibitor control. In this particular panel, there's actually no sample adequacy control, as it's not really required with the intended sample types that we have. So as you can imagine, you can typically see if nail clippings or skin scrapings or hair is being successfully collected. So coming back to this run again, in this case, we have a positive reported for Trichophyton species. So genus level identification, which is the red curve. We also have a positive reported for the Trichophyton rubrum complex, which is the green curve. So this can then be reported to the clinician as confirmation of their initial diagnosis of dermatophyte infection with the causative agent identified as Trichophyton rubrum, all around 3 weeks earlier than they'd normally expect. So overall, I hope I've shown that MT PCR is an effective platform for comprehensive syndromic testing. I hope I've also demonstrated that MT PCR can also be applied to a wide range of diagnostic applications, from respiratory pathogens, STIs, and mycology, as demonstrated. But can also be applied to enteric pathogens, CSF screening, genetic screening, which these are all things I didn't actually have time to present today, but they are other applications of MT PCR. And I hope I've shown that MT PCR can be quite flexible in things such as SNP typing, the identification of insertions, deletions, and so forth, and is also capable of providing useful additional feedback to the clinician on things such as the resistance status of a particular pathogen. So hopefully you found this presentation informative and come away with a better understanding of the MT PCR method, and obviously a few of its advantages. So just before I finish up, I'd like to thank the NRL for putting on this conference, given the trying circumstances we find ourselves in, and allowing us to provide this talk to you today. So thank you all for your attendance. I hope you enjoyed this brief presentation, and I'll pass you back to our moderator. Thank you.